In the last module, we looked at the integral momentum equation, applied it for a case for flow over a flat plate with no suction or blowing, which means uw is equal to 0, constant free stream velocity, which means du infinity by dx is equal to 0. That means the integrated momentum equation went to become d delta 2 by dx is equal to cfx by 2. We assumed a third order polynomial profile, which was given by this one, a plus p eta plus c eta squared by d eta cubed, and we applied 4 boundary conditions to get these coefficients a, b, c and d. It turns out that no slip boundary condition at the wall gave a equal to 0, u by u infinity equal to 1 at the edge of the boundary layer. Third boundary condition was du by dy at the edge of the boundary layer was equal to 0. Fourth was use of the x momentum equation at the wall, which gave me d squared u by dy squared is equal to 0, and I got c also mathematically turning out to be 0, b was 3 by 2, d was minus 1/2. When I went on to do the maths, so my integrated momentum equation was simplified to this form, d delta 2 by dx, this was here, d delta 2 by dx is equal to cfx by 2. So, we put the profile for the velocity, delta 2 definition was used, delta 2 was nothing but u by u infinity into 1 minus u by u infinity. So, I substituted this u by u infinity here, did the maths, obtained the expression for delta 2 in terms of delta. This was the left hand side. So, d delta 2 is nothing but 39 by 280 d delta by dx. Cfx by 2 coefficient of friction was tau wall local Tw of x divided by 1/2 rho u infinity square, and this also did not need any additional work. We had obtained an expression for du by dy in one of the boundary conditions. Evaluate that at y equal to 0 means eta equal to 0. I am left with u infinity b by delta. This times mu, b was 3 by 2, so it is 3 by 2 mu u infinity by delta. So, I substitute this back into the expression for coefficient of friction. I get this. Integrated momentum equation on simplification became this. Do the maths, separate the variables. On separating the variables and performing one integration, we get delta squared is equal to 280 by 13, something which looks like Reynolds number, which on a little bit of manipulation multiply and divide by x squared. So, delta by x the whole square is equal to 280 by 13 re to the power minus 1. Taking square roots, under root of 280 by 13 comes out to be 4.64. And this is so beautiful that exact solution was 5, similarity gave something close to 5. This integral method gives me 4.64. The 4.64 would tend to 5 if I go to a more accurate profile, take a higher order polynomial, maybe 5th order or something like that, but it is not so easy because we need to develop boundary conditions, physically correct boundary conditions to take care of that. Using this, we can write Cfx is nothing but 3 nu by u infinity delta. This was derived. Therefore, Cfx comes out to be 3 nu by u infinity delta is 4.64 x by re to the power 1/2. So, this is a Reynolds number, u infinity x by nu. So, 3 by 4.64 re to the power half divided by re local. This comes out to be 0.646 divided by re to the power 1/2. What was it that we got? It was something like 0.622. So, we are 0.664 I think. So, we are having a number for coefficient of friction very close to what was obtained in exact solution. 0.332 was Yeah, 0.664 was there, we are getting 0.646. With some effort and increasing the complexity of the polynomial function, we would get closer to the exact solution. Please remember, your similarity solution was more laborious. Blashius solution, exact, you had to go to the computer to solve the differential equation. And at this point, we should take a look at what we have seen so far. We started off with scaling analysis. Went on to do Blashius exact solution. Similarity method was an offshoot of that, now integral method. Okay. You can see how logically things are progressing. Scaling gave me a functional form of CF. Is a function of RE alone, right? Non-dimensionalization of the momentum equation gave me CFX is a function of RE alone. I didn't know the coefficient there. Similarly, you got Nusselt number was a function of RE and PR, and for Prandtl number less than 1 or greater than 1, you got the appropriate powers as 1/2 or 1/3. So, Nusselt number was of the order of RE to the power half, PR to the power half or 1/3. We didn't know the coefficient. When I went to similarity solution, I could get a coefficient there. Now, when I come to integral method, I get a coefficient lot easy in a simpler, arithmetically simpler manner, not so accurate, but the functional form still remains the same, RE to the power half, minus half. So, this is something which is unfortunately not taught in undergrad curriculum. Coefficients are presented to students, they are asked to use the appropriate formula. Many times students are asked to memorize this formula for appropriate geometries. This is absolutely incorrect way of handling things, because there is nothing to memorize here. The coefficients, yes, probably you should in fact give this to the students in an exam, but more importantly, test the students on how you got the appropriate power, appropriate functional relationship for coefficient of friction in terms of RE and PR. If it is Nusselt number, it should be RE and PR. Coefficient of friction, it should be only RE. So, how by non-dimensionalization scaling we could get to how the equation looks like, that is so much more useful than by having certain correlations where each coefficient would be different and relevant for a particular application alone. Okay. So, this connect at the end of doing this integral method, we need to bring it out to the students, so that people don't think of this as some black magic or something where some numbers are coming from somewhere. It is not like that. Okay. Now, we go to the derivation of the integrated energy equation. This hopefully we should finish in this module, otherwise we will spill it over to the next module. This integrated energy equation requires another definition of what we call as enthalpy thickness. Enthalpy thickness is given by the symbol capital delta. Capital delta 2 is the definition of enthalpy thickness, and I am not going into the details of the derivation. I will just explain the physical import of it. Let us say this is my thermal boundary layer. I am just showing the thermal boundary layer now, not showing the hydrodynamic boundary layer. Let us say delta is approximately equal to delta T, just for simplicity. So, this is my velocity profile, this is my temperature profile. Okay. What is the energy content of the incoming stream? U infinity T infinity is the pair. Okay. So, the energy coming in is nothing but m dot Cp T infinity, which is nothing but rho U infinity into the area B times dy Cp T infinity, correct, 0 to infinity. This is what is coming in. Of course, rho, B, Cp, everything is constant, U infinity, T infinity is constant, and this would just go from the integration of 0 to integration of dy going from 0 to y basically goes from 0 to delta, delta to infinity. So, this quantity can be obtained very easily. Now, analogous to what was done for momentum thickness, the fluid, because it has a velocity different from the free stream velocity, different from the free stream velocity varying in the y direction, resulted in a momentum deficit given by something like this. Therefore, we had to define a momentum thickness to account for that deficit, conservation of momentum. Now, the same logic is used for energy content and the heat transfer associated. Okay. What is the maximum heat transfer that is possible? The maximum heat transfer that is possible is when Tw minus T infinity is the driving temperature difference. What is your driving temperature difference at every location? It is T of x comma y minus T infinity. Is that right? This is actual. This is maximum temperature difference. Maximum driving temperature difference is this one. Obviously, the heat transfer in this case would be lower than what is maximum possible heat transfer, right? The enthalpy thickness physically accounts for this kind of a deficit, and I am just going to write the definition. It is given by integral 0 to infinity rho Cpu of x comma y. I am putting this x comma y to emphasize that these are all variables, T of x comma y minus T infinity divided by rho Cpu infinity T wall of x, could be function of x or a constant, does not matter, times dy. This is my definition of enthalpy thickness. By how much should this so called boundary layer compensate so as to give you the same total heat removal? Okay. What was your momentum thickness? Delta 2, if you remember this, 0 to infinity, u by u infinity 1 minus u by u infinity dy. Okay. Take a moment and pause and look at what we are doing. This, I just needed the velocity profiles. Very good. We also did the third order velocity polynomial. We got u by u infinity is 3 by 2 eta minus 1 by 2 eta cubed. Went on, substituted, got an expression for delta 2 is 39 by 280 delta, right? The logic is the same. You split this from 0 to delta and delta to infinity. This will go off to 0. So, you are left with 0 to delta. Here also we will do the same thing, 0 to delta, delta to infinity. Now, not so straightforward. Why? I have, see, energy equation is very nice because it's a scalar equation, but energy transport happens because of velocity. So, hydrodynamics and heat transfer are completely coupled. You cannot segregate the two. Why and how it is seen? It is seen by the fact that you have this u and t infinity, u t wall. This pair is going to continue to affect the heat transfer, it's going to go as a pair. That is why I said here I am taking delta equal to delta t, which means my variation in the boundary layer thickness, hydrodynamic and thermal boundary layer thickness are similar. One is not growing faster, other is not growing slower, which means when I have to evaluate this enthalpy thickness, u into delta t, profile for velocity times the profile for the temperature. these two profiles have to be multiplied and integrated. Okay. What was done here? For your momentum thickness, the same velocity profile and 1 minus that was multiplied and integrated. Easy. Here, for enthalpy thickness, I will have to take the velocity profile multiplied by the temperature profile. Now, if both the hydrodynamic and the thermal boundary layer are of similar thickness, same order, delta is of the order of delta T similar, then I don't have a problem at hand. Okay. Otherwise, I have a big problem. Let us see what kind of a problem this is going to be. Of course, no problem is insurmountable, so we are going to see this. This is a flat plate, this is delta, and this is delta T. Another case, flat plate, delta T, delta. All are functions of x. I am not cluttering this figure. X axis, y axis, x axis, y axis, all u infinity, t infinity, all this is standard. So, let us not waste time doing these things again and again. What is this case? Delta smaller than delta T. What is Prandtl number? Less than 1. Prandtl number greater than 1. Let us draw the velocity profiles. Again, we have drawn this many times. We will draw it one more time. Velocity profile is like this, u infinity here, right? U infinity in this part, varying in this part. What about the velocity profile here? Continuously varying. What about the temperature profile here? T of x comma y, continuously varying. What about the temperature profile here? Varying here, constant here. This is not drawn to scale, but this is T infinity, constant. So, unless delta and delta T are growing at the same rate, which is valid only for a small range of Prandtl number, you can see where the complexity comes. U of x comma y times delta T. So, this definition delta 2 0 to infinity rho Cp u x comma y T of x comma y minus T infinity divided by rho Cp u infinity T wall of x, I am putting, it can be constant dy. This has to be split into 3 parts. In this case, PR less than 1 case, it has to go from delta 2 has to go from 0 to delta. I call this integral I delta to delta T, and then delta T to infinity. PR greater than 1 case, this delta 2 would go from, let us look here, 0 to delta T to delta, delta beyond delta. 0 to delta T integrand plus delta T to delta integrand delta to infinity. Correct? Now, this thing, if you look beyond this, beyond delta T or beyond delta, where you are talking only of temperature equal to T infinity, both cases, this is going to drop off. So, everywhere Prandtl number greater than 1 or less than 1, this term is going to drop off because T is equal to T infinity. So, the difference is going to be equal to 0, therefore, the integrand would be 0. Now, for Prandtl number less than 1, I have 2 terms, greater than 1, I have 2 terms. What will be here? Let us look. Prandtl number less than 1. What is the velocity here in this part? It is u infinity by u infinity. Rho Cp can cancel. T minus T infinity by T wall minus T infinity. Delta to delta T. 1. Please go back here. This one. I have just put this in red. Okay. U by u infinity, because beyond delta velocity is u infinity. Beyond delta velocity is u infinity, so it becomes nice. This would be as it is. As it is. Here also this is going to be as it is. But this term, second term, what is it going to be? T is equal to T infinity, so the integrand would be 0 because the numerator becomes 0. So this becomes 0 because delta T less than y less than delta T of x comma y is equal to T infinity. So for the same reason that this became 0, this also becomes 0. So Prandtl number greater than 1, I have to deal only with one term. Prandtl number less than 1, I have to deal with two terms. Okay. So the evaluation of this enthalpy thickness, which is going to be there in the integrated energy equation, one has to be very, very careful in what we are dealing with. When Prandtl number is approximately 1, delta equal to delta T, this whole thing does not occur, but it is always a good idea to write the general form first and then go to the specific form. Otherwise, if I did not do this step by step, I would not know that the second term here would cancel off. I would know only this, and I would be wasting my time and effort in calculating this thing over 0 to delta when it actually needs to be calculated only between 0 and delta T. I hope you are able to understand and appreciate this, and this needs to be emphasized to the students. Okay. So once we have understood the definition of enthalpy thickness, we will just get started with the derivation of the integrated energy equation. Your integrated energy equation follows the same logic as the derivation of the integrated momentum equation. Now you are dealing with two boundary layers, delta and delta T. The H that is chosen is greater than the maximum of delta or delta T. So we do not have to worry about it, and your integrated energy equation is going to be obtained in this manner. Boundary layer approximations were introduced already. So I would write this as u dt by dx plus v dt by dy is equal to alpha d squared t by dy squared plus nu over Cp du by dy whole square. This is advection, this is conduction, this is viscous heating. Important in high speed flows, can be neglected. What we are going to do in this derivation is to keep things as general as possible as we did in the integrated momentum equation. Okay. And then drop off certain terms to 0 to simplify it for flow over a flat plate subjected to constant wall temperature. Okay. So it is always good to have a general expression, then go to a specific case rather than derive separate equation for each specific case and waste our time. Okay. So let us define, now let us just recast this. So let us consider d by dx of ut plus d by dy of vt. This is nothing but u dt by dx plus v dt by dy plus t times du by dx plus t times dv by dy. So this one drops off by continuity equation. Therefore, my left hand side of the energy equation is nothing but this. Therefore, I get energy equation, just as we multiplied, we got d by dx of uu. I am going to write this as d by dx of ut plus d by dy of vt is equal to alpha d squared t by dy squared plus nu over cp du by dy whole square. This is my equation to be integrated. So, let us define now. Theta is equal to t minus t infinity by t wall of x minus t infinity. This I am keeping in general. T wall is a function of x, okay. T wall is a function of x, can be constant later on, okay. So, let us define it this way, and if I put it this way I will get, and also assume t infinity is equal to constant. Therefore, I substitute now for this theta here. So, I will do one term, d by dx of ut is equal to d by dx of u into t wall minus t infinity plus theta, of course, theta plus u times t infinity. Theta is this t wall minus t infinity into theta, that is t. There is a plus t infinity which comes, both of which are multiplied by u. This is going to be this term. So, I can do this differentiation as follows. This is t wall minus t infinity d by dx of u theta plus u theta d by dx of t wall. Why this? Because d by I am going to use this as a pair, this one and this one as one pair, that is why this is taken like this. T wall is only a function of x, t infinity is a constant. So, dt by dt wall by dx is a regular derivative. What is the third term here? T infinity is a constant, so it comes out du by dx. So, this term is nothing but t wall minus t infinity d by dx of u theta plus u theta d by dx of t wall minus t infinity, okay. So, we stop here. Next module we will continue with the derivation of the integrated energy equation and see one solution for the case using a third order temperature profile, and hopefully that will cover all the aspects of the integral equation and show us how simple it is for execution. Of course, there is a lot of good bookkeeping that needs to be done. Nevertheless, it is a very powerful tool to be used in solution of thermal problems. Thank you.